Hello and welcome to the full video about a paper titled Class Prior Estimation in Active Positive and Unlabeled Learning. My name is Lorenzo and I'm from DTI Lab of KU Leuven in Belgium. I have worked on this paper together with Vincent and Professor Jesse Davis from KU Leuven as well. Okay, let's start introducing a general PU setting, which is a special case of semi-supervised learning where instead of having labels from both of the two classes, the labeled examples can only come from a single class that we call positive. PU data naturally arises in many real-world scenarios, and here there is an example. So assume that you're observing click data and you want to measure how relevant the ads can be for a given user. Then every time the user clicks on an ad, you may collect it as positive example. And on the other hand, what conclusion can you draw if the user does not click on an ad? Well, certainly you cannot assume that the ad didn't interest the user, because it might be possible that the user simply didn't click on it for other reasons. Therefore, you cannot label the ad as negative, and it has to be considered as unlabeled. So in this scenario, the real challenge is to exploit the unlabeled ads, which are the ones that the user has not clicked on, to estimate the relevance on the user's profile. The key question here is then, how can we learn a predictive model from PU data? Well, mainly the common approach for learning from positive and unlabeled data focuses on estimating the class prior, which corresponds to the proportion of positive examples in a given dataset. However, in order to estimate the class prior, we first need to make assumptions on the method generating labels. A widely used assumption is the SCAR, which states that the positive labeled sample is an IID sample drawn from the positive population. Therefore, the probability that any positive example is labeled does not depend on its features and is actually a constant that we call label frequency. Then, under the SCAR assumption, it turns out that the proportion of labeled examples is proportional to the class prior through the label frequency. Since the proportion of labels can be directly computed from the data, the goal of several methods for computing the class prior is to estimate accurately this constant C. However, the main issue is that the SCAR assumption does not hold in many practical cases, since many times labels are not collected randomly, and as a result, we introduce a novel scenario where we assume that labels are acquired through an active learning strategy. Using active learning is a way to introduce the user feedback in machine learning, which consists of querying the examples that the models is more uncertain about and exploiting the collected feedback to improve the model's performance. In this scenario, we assume to start from an unlabeled dataset where we can train an unsupervised model. And then, according to the chosen active learning strategy, we select the most informative example, which is the one indicated by the big circle here in the GIF. Then we query that example to the user and collect the label only if it is positive. To visualize this, you may think that the user can only recognize positive examples, while if a negative one is queried, then the answer would be, I don't know the label. By collecting labels this way, examples are no longer selected completely at random, because the active learning strategy has a clear bias when selecting the examples to be labeled. As a result, the label frequency C is no longer constant because the probability of collecting any label depends on the features by the chosen active learning strategy. In this paper, we make 4 contributions. First, we formalize the problem of estimating the class prior, which is the proportion of positive examples, in the scenario where labels are collected through an active learning strategy. Second, we propose CAIP, a model which can estimate the class prior in this setting by computing the contribution of any positive examples and merging them together. Third, we prove that CAIP's estimate of the class prior converges to the real expected value. And finally, we evaluate CAIP on 9 anomaly detection benchmark datasets, where we consider the normal examples as positive, and consequently, the class prior is the proportion of normal examples. Our first contribution is to formalize the active learning in a PU setting. Assuming that the user can only provide positive labels, we distinguish two behaviors. In scenario 1, the user is perfect and always labels only the truly positive examples. This means that when a negative example is queried, the user in scenario 1 always replies, "I don't know," the label, and the example remains unlabeled. Whereas in case a truly positive example is queried, the correct positive label is always provided. On the other hand, in the second scenario, the user is more human and may make mistakes in two directions. When a negative example is queried, the user in scenario 2 can either reply, "I don't know," or label it wrongly as positive. Likewise, when a positive example is queried, the user in scenario 2 can provide the correct positive label or wrongly reply, "I don't know," leaving it unlabeled. In the paper, we practically model the user's uncertainty in scenario 2, allowing this possibility of making mistakes. So now the question is, how to estimate the class prior in such two scenarios? Well, in order to estimate the class prior, the key strategy is to measure the contribution of each example in the dataset. Under the scarce assumption, unlabeled examples have the same contribution, and it equals the label frequency C. Therefore, the goal of many approaches is to measure accurately this constant C in order to derive the class prior by dividing the proportion of positive labels with respect to the full dataset by the proportion of positive labels with respect to the positive examples, which is again the label frequency. As I already said, collecting labels through the active learning strategy violates the scarce assumption, and the displayed formula can no longer be used. So the question here is, does the contribution change when collecting labels via active learning? In order to answer this question, let's introduce the propensity score, which measures how propense an example is to be labeled in a probabilistic sense. And since this probability strictly depends on the active learning strategy, examples do not have the same propensity score. Remember that the only way to obtain an examples label is by querying it to the user. And it might be thought that the greater the propensity score, the more likely an example is positive, and as a result, the greater is the contribution. This is not fully correct though, because if the model is almost certain that an example is positive, then the active learning strategy will not query that example to get its label, and consequently, it will get low propensity score. So how to quantify the contribution of each positive example in the dataset? Let's assume for a while that the propensity score is known. Then we can derive the class prior by weighting each example differently and taking the average as result. We distinguish the contribution of labeled and unlabeled examples. Regarding the labeled positive examples, each of them contributes fully. And to visualize this, suppose that we query as much as possible and that all the positive examples are therefore labeled. Then, by simply counting them and dividing by the dataset size, we would get the class prior, which is exactly what the first piece of the equation claims. On the other hand, the second term contains the contribution of unlabeled examples. Assuming that the model produces accurate and calibrated probabilities y hat, unlabeled examples contribute by their probability to belong to the positive class, weighted by their propensity score. How do we read this value here? Well, it represents a trade-off between the case where the propensity score is high and the posterior probability is low, with the case where the posterior probability is high and therefore the propensity score is low. As we have seen so far, the propensity score is definitely relevant for computing the class prior. So how can the propensity score definition be adapted when using active learning? Remember that the propensity score is defined as the probability that a positive example is labeled. And under the scarce assumption, it is constant and equal to the label frequency C. However, in our scenario where labels are collected through an active learning strategy, the propensity score depends on the informativeness of the example. In addition, since the only way to get the label is by querying the example to the user, The propensity score can be seen as the probability that a positive example gets selected to be queried to the user. So how can we estimate the propensity score in practice? Well, first, I'd like you to realize that the propensity score is a continuous probability measure spread out across the feature space and does not sum up to 1 if we narrow it down to the examples in the dataset. Then our key insight is that for a given dataset, the active learning strategy selects deterministically the examples to query, and as a result, the propensity score given a dataset is either 0 or 1 for each of the examples. You may see this by thinking that if we could query 5 examples, then the 5 most informative examples, according to the model, would be selected to be queried, while the remaining would not. However, the propensity score refers to the distribution of positive class. We could tackle this issue by drawing subsamples as many times as possible from the dataset, and each time we say whether each example is queried or not. Indeed, this would simulate dealing with distribution. As a result, the propensity score would be the proportion of time examples get queried when drawing subsamples. Instead, given that this procedure may be expensive, we apply combinatorics rules and use the average to approximate the probabilities. This certainly saves time despite introducing some approximation errors. Besides, this procedure depends on whether user 1 or user 2 is involved, as in the second case, we should also take the possibility of making mistakes into account. Okay, let's pass now to the third contribution. Theoretically, we analyze the convergence of our estimates. In the paper, we prove that the number of subsamples that we should draw is actually countable, so that we can apply combinatorics rules as a result. Then we prove that our propensity score estimate converges to the real function when increasing the number of drawn subsamples. And finally, the estimate of the class prior converges to the real value when the propensity score gets more accurate. For further details, have a look at the paper where you can find the proofs as well. Regarding the experiments, in the paper we addressed three different empirical questions. First, we show that CAPE can recover the class prior better than the baselines. And second, we test our method both in scenario 1, where the user is a perfect oracle, and in scenario 2, where the user may make mistakes. And finally, we analyze the difference in performance when an anomaly detector uses a more accurate estimate of the class prior. Here, I only discussed the first question, but feel free to read the paper for further details. About the experiments, we applied our method on anomaly detection, where the positive class is the normal one. Given an anomaly detection model, we query 5 labels at the times, and at each step, we estimate the propensity score and use it to derive the class prior until a total of 150 labels are collected. The plots show the error in the class prior estimate, and as a result, the lower, the better. We tested CAPE on 9 anomaly detection benchmark datasets, having different values as class prior. Comparing CAPE with the state-of-the-art baselines, it turns out that our method performs better when the user in scenario 1 is asked to provide labels, while sometimes other baselines might be preferred when the user in scenario 2 is involved. Overall, our method is certainly more stable compared to the baselines, showing less fluctuations. In conclusion, we introduced this novel scenario where PU learning is combined with active learning. We propose CAPE, which is able to estimate the class prior. We prove theoretically that our estimate converges to the actual value, and we empirically show that the CAPE accurately recovers the class prior in practice. For testing CAPE, use the code available at my GitHub page and have a look at the paper for further details. For any question, don't hesitate and send us an email, and thanks for your attention.